Okay. So okay, I heard some discussion says if you cut it open, there are gonna be small holes or small empty space inside. Someone, did you guys mention that? Any other imperfections you can think of? Yeah, so this is aluminum bar, but there could be other atoms get mixed into this aluminum bar. Could be copper, iron, or other metal elements, or could be non-metal atoms get mixed into this aluminum bar. And well, that's good. That's deep into the atomic level. But just it looks very smooth. But when we look at this metal bar under microscope, and you will start to see the scratches on the surface or small, tiny holes on the surface. So the surface is not smooth when you zoom in. Look at the microscope image of this aluminum bar. And that's actually, since the material engineer is a relatively new engineer. So back in days, people don't really have a good understanding about atoms, crystal structures. So all the perfections, they think it's just, okay, when you cut it open, there's some small holes. When you look at this image under microscope, there's some roughness, there's something not belong to this aluminum for the inside. But with the development of material science, we're looking into the atomic level to look at atoms, aluminum atoms, and look at the imperfection inside of the crystal structure. That's what we're gonna talk about today. But I have a question. Before we talk about imperfection in solids, are imperfection bad or good? Is a good thing or bad thing? Okay, 2 minutes, talk to each other. Is a good thing or bad thing?
There's material, right? And it's gonna fracture the point. If it's perfect, it'll fracture like this. It'll have the easiest way to get across. If it's perfect, it obviously won't be this. It won't be here. I can still imperfect be stronger than probably the back to the right. No, nothing perfect makes me better.
Okay, so even you learn nothing from this chapter, but at least one thing you should remember is pure materials don't exist. There's nothing is called pure materials. And also the question, that's one thing to remember. Another thing is the answer to the question, it's are imperfections good or bad? It's not, they're not necessarily bad. It could be a good thing. I'm going to give you an example to show you how come imperfection can be a good thing. Once we understand imperfection, we can manipulate materials to make them the way we want them to be. So let's look at an example. We have almost pure copper. Let's see, we have copper that is 99.99% pure copper. And so that 0.00101 could be some defects. And for this 99.99% copper, the mechanical property of this copper, let's look at yielding stress. Sigma Y. For this copper, the yielding stress is about 4,830 psi. And the ultimate tensile strength, the maximum stress on the stress strain curve, TS, it's about 3,500 psi. Okay, so the same copper, if we cold roll it, cold rolling, that's one of the treatment we can do to the copper. So when we use treat cold rolling, we are adding imperfections into this copper. So we're adding, we're gonna learn this later, but actually the cold rolling introduce dislocations in fact. This is a part of a kind of defect. So right now, after this treatment, the yielding stress, sigma Y, becomes 48,400 psi. And the ultimate stress is 49,900 psi. Just from the mechanical engineer perspective, we're adding some dislocation defects, and we're ending up with a material with higher yielding stress and higher ultimate tensile stress. Well, if we're building things, we want to see those numbers as high as possible, right? So adding defects actually increase the mechanical performance of this material. And right, we can do something more to this copper. Now let's add some impurity. Let's add 1.7%. How do you call this? Beryllium? Beryllium? No, beryllium. And nickel. Add some beryllium and nickel. It's Nike. And plus some heat treatment. So right now we're adding impurity as a defect. So right now, this copper with mix of beryllium and nickel will give you yielding stress as high as 180,000 psi. And the ultimate tensile strength, it's about 200,000 psi. So what do you see here? By adding imperfections, we're seeing increased performance. So that is same thing happening to iron. If we add a little bit carbon into iron, then we end up with steel. Steel is much stronger than iron, pure iron. So we're adding impurity to iron, we end up with steel, which is much stronger. And we add some chromium into iron, we end up with some stainless steel. That's even better. So we're adding impurity, which is kind of defect, into the material, but turn out we got some better performance from those materials. So imperfection is not necessarily a bad thing for material. Okay, so let's talk about types of defects. So in solid materials, we have 4 different types of defects. I'm going to focus on 2 of them, 3 of them probably. The first type is called point defect. And second type is called line defect. And can you imagine what's the third type of defect? Now you have point, you have line. The third, yeah, you have, now we're looking at more big area. You have an area defect. Or it's also called interface facial defect. And the last type is, all right, now you have area. We can have a volume, whole volume of defect. It's called bulk defect. Or you can also look at this a different way. Point defect, that's kind of like a 0 dimension, 0D. And line defect, now you have 1D. For the area defect, it's kind of like 3D. Bulk defect or volume defect, you have 3D. And actually from the last chapter, we touched a little bit about area defect. Under here, we learned that green boundaries, that belongs to area defects. Okay, so we have these 4 different types of defects, and we're gonna put a little bit more focus on the point defect. So here for point defect, we have one kind of point defect is called interstitial defect. The second type of point defect is called substitutional defect. Okay, and when under line defect, we have something called dislocations. All right. Okay, so the first thing we're gonna want to look at, focus on our attention to point defects. So before we talk about point defects, we're gonna do something fun. we want to figure out if you have a piece of metal, we want to use the equation to figure out how many atoms in this piece of aluminum bar. So if I give you dimension of this aluminum bar, the radius, the length, and we're gonna use the equation to figure out how many aluminum atoms inside of this bar. If we assume everything is ideal, there's no defect, there's no void space inside. Questions? The interstitial. Yeah. The second one is substitutional. Okay. First thing we want to do is find out number of atoms per unit volume. For metal. So this number of atoms, we use capital N for the number of atoms. So the equation is that N, the number of atoms per volume, equals Na times rho divided by A. So here, Na, it's called, remember what is Na? We met Na one time. It sounds like a type of food for your breakfast. Avocado number, remember that? We use our avocado number for our density calculation. So Na is the same thing. And it's a constant number, 0.02 times 10 to the 23rd. The unit is atoms per mole. It's a constant. Rho here is the density of the material at a given temperature. And A here, it's the atomic weight. So now we know all the variables inside of this equation. You can find out A from periodic table. All the atomic weight are listed there. Okay, let's look at an example. The example is copper. If we have copper at 1000 degrees, and how many atoms we have inside of unit volume? Okay, at 1000 degrees, a unit volume of copper, just give a wild guess. How many copper atoms in a unit volume? Just guess the magnitude of N. This time is for copper. Just give a wild guess. Think about if you just, instead of a one, let's use a realistic volume here. 1 centimeter cubic space. Oh, that's probably smaller than this bar. How many atoms, copper atoms, could be inside? Millions, trillions. So let's do the calculation to figure out how many atoms are inside. So in order to find out how many copper atoms, we can apply that equation. So Na, that's Avogadro number, times rho copper, divided by atomic weight of copper. And we can plug in all the numbers we know. So the avocado number is a constant. So when you do calculations, make sure you add all the units. And the density of copper at 1000 degrees is about 8.49 grams per cubic centimeter. And the atomic weight for copper is constant. It's 63.5 grams per mole. Okay, since here, let's convert the centimeter to meter. So that is 10 to the 6 centimeter cubic divided by meter cubic. Okay, if you have a calculator, you can plug in numbers to see how many copper atoms in a cubic meter size. So the final answer should have the unit as atoms per cubic meter. So if you have a 1 meter by 1 meter by 1 meter cube, and that copper is that size, how many atoms you have? Nine 9.18 10 to the 21. 10 to the 21. Okay, that's a little bit different than what I have here. Maybe I'm really bad at calculations. I could make a mistake here. What I have is 8 times 10 to the 28th. Okay. Well, what is that called? That's not millions, right? Millions only to the 9th. So I didn't know what's that called. So I look up on Wikipedia. That's octillion. Octillion is 10 to the 27th. So that's a very large amount of atoms instead of 1 cubic meter metal cube. Okay, so several things in this calculation. The equations are not bad, pretty easy. The density you applied in this equation must be the density under that temperature. As we know, the density changes as temperature changes. So here we're talking about 1000 degrees to make sure that's the density under that temperature. Okay, so at this temperature, this is the amount of copper atoms we have. Okay, so now we know ideally how many atoms should be inside of 1 cubic meter. Now we want to find out how many atoms are missing. So like I said, there's no perfect materials. So inherently, there are missing atoms inside of this metal cube. So the equation for number of vacancy, that's point defect. The equation is, we use NV to represent the number of vacancies, number of missing atoms. So NV equals N. N is the total number of atoms per unit volume. That's the same N as what we did in the last example. x times exponential negative qv divided by kt. So let me explain what is qv here. So here qv, it's the energy that is required for vacancy. And the unit for that is joule per mole, or you can use a different unit. We can use electron volt, EV, per atom. That's kind of tell you how much energy that's required to take one atom off from that crystal site. That's QV. So remember, QV has two different units. You can express QV as joule per mole, or you can express QV as electron voltage per atom. Okay, now let's look at K. K here is a constant. It's called Boltzmann's constant or gas constant. Constant is 1.38 times 10 to the negative 23rd. The unit is joule per atom times Kelvin. Yeah, it's 38. And also this constant number could have a different unit. It also equals to 8.26 times 10 to the negative 5 electron voltage, electron volt divided by atoms times Kelvin. Okay, so that's a constant number too. T here is just temperature. That at the temperature, the same temperature, you're looking at the vacancy. So that energy required for vacancy, that is also function of temperature. So at different temperature, the energy required to form a vacancy is different. Okay. Now let's wait, one more thing. This temperature T should have unit as Kelvin instead of Celsius. So just look at this equation. The number of vacancies increases if temperature rise. You see that? That's exponential. And then T, if T is large and that whole number is large, give you large MV. So temperature, you can think about temperature as an energy, right? The higher the temperature, the more energy atoms get. And the higher the energy, then easier to form more vacancies instead of solids. So remember that NV increases exponentially with temperature. There's a good example to show this. At a very high temperature, most of the metal will, if at a really high temperature, it will melt, it will turn into liquid. But right before the melting temperature, 1 out of 10,000 crystal site would be empty. So think about if you have a perfect crystal structure. 1 out of 10,000 site inside of that crystal structure would be missing. So that's kind of how many missing atoms you're gonna have. So right below melting temperature. One out of 10,000. Or we call lattice site. That's the position inside of crystal structure that should have atoms, but at this temperature, one of them would be empty. So pretty much we know if any piece of metal, there are missing atoms inside. If the temperature is higher, there are more missing atoms. That's what we pretty much know from the two equations so far. And now let's do a practice to say how many missing atoms are from the same copper at 1,000 degrees. So we know the total atoms inside of this 1 cubic meter copper cube, it's about 8 times 10 to the 28th atoms per cubic meter. We want to know how many missing atoms, how many vacancies inside of this number. So let's look at the calculation. NV, that's a vacancy number equals N. We want to know that's a total number of copper atoms times exponential negative QV divided by KT. Okay, I'm plugging numbers. It's 8 times 10 to the 28th. Unit is atoms per cubic meter times XP. Plugging. So at that temperature, the energy required is about 0.9 electron volt EV per atoms. Oops, I think divided by K, which is Kelvin of 1,000 degrees. 1,000 degrees equals 1,273 Kelvin. And K is a constant number, which is 826 times 10 to the negative fifth EV per atom K. Okay. So one thing to pay attention when you do this, the equation is pretty straightforward, but the unit can be tricky. Since here the energy required for vacancy QV, it's given as volt per atoms. So when you use K, you want to use the K value that has the same unit as electron volt per atoms times Kelvin. Remember previously we have two numbers for this constant that are in different units. Here we use the unit of EV per atoms times Kelvin. So if you have a calculator, you can try to find out what's the number of vacancies. if my calculation is correct. I got this amount of vacancies per meter square. So we have a lot of vacancies in the material. Okay, make sure you remember this. Vacancy. It's significant. And it is also inherent. We can't really get rid of vacancies. They just always come with the material. No matter what you do, there's always vacancy in the crystal structure. They're always missing atoms. So for example, if this aluminum has FCC, face center cubic structures, and it's pretty possible that inside of the crystal structure, some of the atoms at the corner of the unit cell is missing, some of the atoms at the face is missing. So as temperature increases, there more and more atoms are missing in the crystal structure. Okay. All right. That's the two equations for today. One is about how to find the total number of atoms per unit volume. That's this equation. Once you have that equation, you can find out what is the total number of vacancies per unit volume. That's the second equation right here. Okay, any questions?
Material like you were talking about before with the polarium and nickel and copper, is that fill those vacancies then?
That's a good question. So at the beginning, we talk about if we're adding some impurities into the material, that make material stronger. But where are those impurities go, right? So there are a couple ways. That's a topic for the, do we have time? Yeah, I think we can have time for this. So type of impurity. If you have impurity, there are two types. The first type is called substitutional. That means it's the foreign atoms replace the host atoms. So in that example, we have copper. We mix that with beryllium and nickel. If this is type of the impurity, substitutional, that means those foreign atoms will replace where the copper atom is supposed to be. And there's another type of impurity, which is called interstitial. That's when you have a smaller foreign atoms, impurity atoms. They were fit in the space in between the host atoms. Remember the either FCC or BCC structure? We have void space. There's so much empty space inside of crystal structure. So in this type of impurity, interstitial impurity, the small impurity atoms were fit into those void space. That's the case for steel. So copper, carbon atoms is much smaller than iron, so it fits into the empty space in the crystal structure. So that's the two types of impurity we have. And let me write down examples. Copper in iron. For the substitutional, the good example is nickel in copper. So nickel atom and copper atom, they're similar size. So they will replace the position of copper atoms. That's the substitutional impurity. Okay, that's all we need to know today. Next time, we're going to talk about more details of these two different types of impurity. That's all for today. All right, you guys have a good weekend. Stay safe, don't go party.